Hello, my name is Jonathan So, and I will be talking about buoyant force. So first of all, I'm going to start by drawing a pool and the deep end of a pool with a pair of goggles in there and a person. So if you have ever tried to swim down to get a pair of missing goggles, then you probably would have noticed a force that pushes on you, and this is known as the buoyant force, and this is the force that causes it to be difficult to go and get those goggles. So we will call it the upward force. Okay, so now I'm going to talk about why this buoyant force happens. So we're going to draw the diagram of a pool. So let me just get out my blue. Okay, so I'm going to draw a can of soup. And this can of soup is going to have, when it's submerged into the water, it's going to have a downward force acting on it and an upward force acting on it, as these purple lines are drawn in. So the white line on the left of the soup can is the total depth of the soup. So the top of the soup can, there's the weaker pressure, and the bottom of the soup can has the higher pressure. So knowing from our formulas, we got P gauge is equal to PGH, which is rho GH. So it will increase with the depth of the soup, or the depth of the object. Okay, so now we're going to write a relationship for force buoyancy, which is going to be equal to the upward force and subtracting the downward force. So knowing that we got, so knowing P is equal to force over area, so the pressure is equal to the force over area, we can simplify this relationship into force is equal to P times A. So now we go further and we write force buoyancy is equal to pressure of the bottom part of the soup can multiplied by A minus pressure times at the top multiplied by area. So writing this even further, we get the buoyancy force is equal to rho GH of bottom multiplied by the area minus rho GH of the top height multiplied by area. So factoring this out, we get force buoyancy is equal to rho GA multiplied by H bottom minus H top, the height of the bottom portion of the can minus the top height of the can. So we are going to draw in this pool yet again. So we draw in our water level, and then I draw my soup can, and then I'm going to draw in the depth of the surface to the top of the soup and the depth of the surface of the water to the bottom of the soup. And then we got this red line, which represents the change in height. So the height bottom minus the height of the top. And this is the difference in height of the can. Okay, so moving on. So we got force buoyancy, which is going to be equal to rho GAH of the can. So the force buoyancy, we know that, interestingly enough, that area times the height of the can is equal to the volume of the cylinder. So now that we know that this is equal to the volume of the cylinder, we can say that this replaces the volume of the cylinder, just to write that out. Okay, so now I'm going to draw in this diagram yet again of the pool of water, and I'm going to draw in my can of soup. So on this can of soup, I'm going to draw the height of the surface of the water to the bottom of the can, and now I'm going to actually move this up. There you go. So it just accurately represents what it should look like now, and then I'm going to draw the upward forces acting on the soup, and as we can see that there's no pressure acting from the top, and so we can write in the relationship that the force buoyancy is equal to rho GA, but this time, and we're just going to move down there, and this time we're going to write the height of the bottom minus 0, since there is no height at the top of the soup can. Okay, so now we go and write in our relationship of force buoyancy, which we now know is equal to rho G V of the fluid. which can also be rewritten as rho GV of the soup can. So all in all, we get the final formula for buoyancy force, which is equal to rho GV of the fluid, F.